I'm Anthony. Today, our topic is from Gaussian process to neural tangent kernel. This topic is about Gaussian process, kernel, and how they relate to deep neural networks. First, we will have an introduction to the stochastic process named Gaussian process. Then discussing about how the infinitely wide deep neural network is equivalent to a Gaussian process. In the last section, we'll go through a theoretical tool, neural tangent kernel, that help us to analyze the training dynamics in deep neural networks. We will also talk about a library called neural tangent that help you implement NNGP and NTK in the last section. Gaussian process, GP, is a stochastic process. It is a collection of random variables indexed by time or space. Those random variables follow multivariate Gaussian distribution. Gaussian process is very useful in many different scenarios. For example, like supervised learning, unsupervised learning, or Bayesian optimization. Since Gaussian process is a stochastic process, we first define what is a stochastic process. Let omega s f sigma p be a probability space with sample space omega s and sigma algebra f sigma and probability measure p. The index set x is a subset of Rnx with positive integer nx. Then the collection of random variable fgp of x and omega s is called the stochastic process. Here we'll simplify the fgp of x omega s as fgp of x. Gaussian process is a stochastic process that can be fully described by its mean function and covariance function. The random variable fgp of x is drawn from a Gaussian process gp with the mean function m of x and covariance function k of x and x prime, where the m of x is the expectation of random variable fgp of x, and the covariance function k of x prime is the expectation of the product of fgp of x minus its mean and fgp of x prime minus its mean. Gaussian process can be used in Bayesian inference as a prior distribution. This is called Gaussian process regression. The prior Gaussian process model is updated with training data to obtain posterior Gaussian process distribution. We'll then show how to do Gaussian process regression in the following. Given the training data set D equals to the x and y, where the input metric x trend is x1, x2 to xnd, and the output matrix y trend is a y1, y2 to ynd transpose. Suppose the output is generated from a Gaussian process plus a Gaussian noise, mu, and mu is a Gaussian distribution with zero mean, and the variance is sigma n squared. Then we can write the yi, the output yi equals to the fgp of xi plus mu. For any test input x prime, we can write the joint distribution. The y, the training data y, and fgp of x prime. This is the prediction, the the data we want to predict. It's from a normal distribution, a Gaussian distribution with mean m of x1 to m of x and d and m of x prime. And the variance consists of 4 metrics. The first one is k of x prime. K, the covariance matrix for the kij of x, it's in fact the k of xi and x data xi and xj, and plus, and the next one is the k tilde x prime x. The k tilde of x prime x is in fact the covariance k of x prime to every data point x1 to x and d. So, and the last one is, and the third one is k tilde x prime x transpose. And the last one is k of x prime and x prime. And this metric, we will rewrite it as sigma. And sigma is have 4 components: sigma 11, sigma 12 transpose, sigma 12, and sigma 22. To compute the posterior distribution and predict f of gp of x prime, we condition on x prime and training data x and y. So this is the distribution we want to predict. The fgp of x prime given the test data x prime, our data set x and y, and apply the Bayes rule, we can divide it into 2 parts. The first one is fgp of x prime and y given our x prime and x. This is a joint distribution, write it above. And the second part is the y value given the data set y given our x prime and training data x. Both the numerator and denominator are multivariate Gaussian distribution. For the numerator, the joint distribution of fgp of x prime and y given our x prime and x is equal to 1 divided by 2 pi to nd plus 1 divided by 2 times the root of determinant of sigma, and this times to exponential of minus 0.5 times y prime minus m of x transpose and x prime and transpose times the inverse of sigma times the y prime minus m of x transpose x prime. Notice that the y prime is the combination of training data y and the data we want to predict fgp of x prime. And the denominator y given x prime x is 1 divided by 2 pi to nd divided by 2 times a root of determinants sigma 1 1 and times the exponential of minus 0.5 times y minus m of x transpose and take transpose of it, and times the inverse of sigma 1 1 and times the y minus m of x transpose. By the help of Schur complement of the matrix sigma, we can solve the exact form of the distribution. The FGP of x prime given the data set x and y and our test data x prime is in fact a Gaussian distribution. And the Gaussian distribution with mean m2 bar 1 is equal to m of x prime plus sigma 1 2 times the inverse of sigma 1 1 times y minus m of x transpose. And the covariant function is sigma 2 2 bar 1 is equal to sigma 2 2 minus sigma 1 2 times the inverse of sigma 1 1 times the sigma 1 2 transpose. That is, we can compute the analytical solution for test data with Gaussian process regression. And we can write the exact formula down. The mean function is m of x prime plus k tilde of x prime and x transpose, and times an inversion of a matrix. The matrix is k of x and x plus the Gaussian noise delta n squared times the identity matrix IND, and times y minus m of x transpose. And the variation function of the predicted data is k of x prime and x prime minus k tilde of x prime and x transpose times the inverse of the same matrix times k tilde of x prime x. To make things more clear, we'll show a simple example of Gaussian process regression. For example, if we have a Gaussian process with the mean function m of x equals to 0 for all x, and the variance function k of x prime equals to 0.3 times exponential of minus x prime squared divided by 5.2. So our data is described by the correlation of different data points. And we have a very small training data with 2 points. So the x1 and x2 is 1 and 5, and y is 0.3 and minus 0.4. Suppose our test data x prime is 2, and we have 0 Gaussian noise. Then we will compute the k of x and x first. So we will calculate element by element. So the first element here, we can compute with this formula. The 0.3 times exponential of minus 1 squared divided by 5.2, it's 0.3. So we write it down. And then we write the next element. It's 0.3 times exponential minus 1.1 minus 5 squared divided by 5.2. It's 0.0138. And we write it down. And because k is symmetry, so we write the last 2 elements. And k tilde of x prime x is, the first element is 0.3 times exponential of minus 2 minus 1 squared divided by 5.2. It's 0.2475, write down. And the next element is 0.53 0.0531. Also write it down. Then we can compute the mean of the predicted f Gaussian process of x prime given our test data x prime and our test training data x and y. It's equal to m of x prime, and this is equal to 0, plus the matrix. We can put it right here, and then finally we can compute it as minus 0.1898, and then we'll compute the variance of the same predicted FGP of x prime. It's 0.3 minus 0.21, it's 0.09. In order to fit a more complicated data set, we can extend linear Gaussian process regression with a kernel transformation. This transformation will represent data in high-dimensional feature space. For a nonlinear feature map phi that is mapped from X to F, where F is a functional Hilbert space, the Gaussian process regression kernel function is k of x prime. It's equal to the inner product of phi of x and phi of x prime. We can compute the Gaussian process regression in nonlinear feature space as long as we have this inner product of Gaussian process, this inner product of phi of x and phi of x prime. Back to 1996, Neal had already shown that under certain conditions, random shallow neural networks with one hidden layer converge to a Gaussian process. Following that, many studies prove that any random, wide, fully connected with any depth hidden layer neural network converge to a Gaussian process as hidden layer width grows to infinity. We can then use the infinite width neural network equivalent Gaussian process as a prior in Bayesian inference. We will roughly go through the concept and show how the training and testing works in this section. We'll start with neural network setup. Consider we have a L hidden layer neural network with hidden layer width NL, pointwise nonlinearity sigma with input x, and our weight is WL and bias BL. Our Gaussian distributed drawn IID with zero mean and variance delta W squared over NL and delta B squared. The pre-activation alpha tilde L and activation output alpha L are defined below. The alpha tilde L plus 1 I of x is the summation of WLij times the activation previous layer activation alpha L j of x plus the bias BLI, and the activation output alpha L of x is equal to sigma of alpha tilde L of x, the pre-activation. And for the first layer, the alpha 0 of x is in fact the input x. For a hidden layer neural network, the output component of this network will look like this. The output is alpha tilde 2i of x, and it's the summation of W1ij times the sigma of a summation of W0jk times xk plus B0j and plus B1I. And this because for the W1ij, this is a random variable drawn from a Gaussian distribution, and the part inside sigma is in fact the alpha 1j of x. It's independent with different j. And the last one, B1I, is also a random variable of a Gaussian distributed random variable. So the overall alpha tilde 2i is in fact a linear combination of IID random variable. Thus, it follows the central limit theorem in the limit of hidden layer with n1 goes to infinity. It will be Gaussian distributed. Therefore, any finite collection of the alpha tilde 2i of x will have a joint multivariate Gaussian distribution, or we can say the alpha tilde 2i of x is drawn from a Gaussian distribution with the mean m1 and the covariance k1. And the m1 of x is equal to the expectation of this random variable alpha tilde 2i of x. This is equal to 0 because W1ij is in fact 0 mean, and this B1i is also 0 mean. And the k1 of x prime is the expectation of alpha tilde 2i of x times alpha tilde 2i of x prime. And this is equal to the delta w squared times the expectation of alpha 1i of x times alpha 1i of x prime plus the delta b squared. So to solve the exact form of k1 of x, we need to compute the expectation of alpha 1i of x times alpha 1i of x prime. We need to specify the nonlinearity sigma in order to compute this value. For some sigma function, such as ReLU, we can in fact solve it analytically. So we will show how to solve it. We have the expectation is equal to 1 over n1 and summation of two ReLU value inside. And we will change the variable in order to do the following step. We'll change the variable like this. The W tilde 0i is equal to change the scale to a root of d in over delta w squared times the wi 0, and we also merge the bi part inside this weight. So it's 1 over delta b times b0i, and the x tilde is root of delta w squared divided by d in x, and sigma delta b. The reason why we do this is we want to make the w tilde 0i to be a zero mean and univariate random variable, and to drop the bias also. And so we can change, after we change the variable, we can write it again. It's in fact h of w tilde 0i dot x tilde, and times the w tilde 0i dot x tilde, and times h of w tilde 0i dot x tilde prime times w tilde 0i dot x prime. And the h of z is the Heaviside step function. It looks like this. It's 0 before for z smaller than 0, and it's 1 for z larger than 0, and it's half when z is 0. And in the infinite width limit, we can now change we can now write this again into this function. Notice that now we add a r here, and the r is equal to 1. The reason why we added r because we'll show it later. Okay, and this it's in the infinite width limit, it's in fact integration. We can do it the integration over a Gaussian distributed random variable w, and because it's zero mean and univariate, so we can write it like this. And this integration is in fact Arc-Cos Kernel. It's 1/2 times the Arc-Cos Kernel of x tilde prime. This Arc-Cos Kernel function has analytical solution. For Arc-Cos Kernel function with r, the analytical solution is 1/pi times x norm to r and times x prime norm to r times a function jr of theta. The theta here is the arc cosine of our x, and the inner product of x and x prime over x norm and x prime norm. And the jr of theta is looking like this. And we can compute, for example, the first two expression. The first two expression, J0 is pi minus theta, and J1, this is the Raoult case, r equals to 1. It's sine theta plus pi minus theta times cosine theta. So we can finally write the exact form of k1 of x prime. It's the delta w squared over 2 pi times k0 of x times k0 of x prime, and take a root of it, and times sine theta 0 plus pi minus theta 0 times cosine theta 0 plus delta b squared, where the k0 of x prime is in fact the expectation of alpha tilde 1i of x times alpha tilde 1i of x prime. This is delta b squared plus delta w squared of x dot x prime over d in. Ding is again the input dimension of our input, and theta 0 is the arc cosine of this one. So in sum, for infinite width one hidden layer neural networks with Relu nonlinearity and randomly initialized weight, we can write down the equivalent Gaussian process with exact mean and kernel function. Then we can extend the result to multilayer neural networks. For L hidden layer neural network, we can show that the output component alpha tilde L plus 1i of x is also a Gaussian process. The mean function of ML of x of this Gaussian process is 0. And the covariant function KL could be computed recursively. It's equal to delta W squared over 2 pi times the root of KL minus 1 of XX times KL minus 1 of KX prime X prime times sine theta L minus 1 plus the pi minus theta L minus 1 times cosine theta L minus 1 plus delta B squared. Here, the theta L is arc cosine of KL of XX prime over the root of KL of XX times KL of X prime X prime. You can see that the function KL of X prime is in fact a function. You can write it as a function with 3 variables, the FL function. The first variable is KL minus 1 X prime. And the second is KL minus 1 XX. And the third variable is this is L minus 1, and this also KL minus 1 of X prime. So we can compute infinite width hidden layer neural network as Gaussian process with 0 mean and KL recursively from K0, K1, and to KL. With infinite width multilayer neural network Gaussian process prior, we can predict the distribution of output FGP of X prime of the neural network given your training data set XY, and we can take the solution from our last section. The data we want to predict the FGP of X prime given your X prime and training data XY. It's the Gaussian process of M prime and K prime. The Gaussian process, the mean function M prime is, you can write it as this. And because ML of X prime is 0, so you can simplify it to this one. And K prime is this one, where the K tilde Li of X prime X is equal to KL of X prime from XY from X0 to XND, and KL Ij of X is equal to KL Xi Xj, and the delta epsilon squared is some Gaussian noise. We call the Bayesian inference with Gaussian process equivalent neural network Gaussian process, or NNGP. The NNGP computational time complexity consists of 2 parts: computing KL and the Gaussian process regression. Simple Gaussian process regression time complexity is in order cube, n cube. But there exist many approximate algorithms that can reduce the time complexity to n squared n, with some m much smaller than n. And the numerical algorithm for computing KL with binwise pre-activation has time complexity like this. It's in order ng squared L times n squared train plus n train n test. And the ng here is the binwise pre-activation output consists of ng elements. We'll explain it later. And the L is recursive, how many layers you have, because you need to compute it from K0 to KL. And last part is for each X and X prime pair in training and test data. And by pipelining and preprocessing all input to have identical norm, we can improve the algorithm to the order of ng squared ns nc plus L times n squared train plus n train times n test. The ns here is binwise variance consists of nv elements, and the nc, this is ns element, and the nc here is binwise correlation consists of nc element. Although with Raoult nonlinearity, we can do Bayesian prediction analytically. But for most of nonlinearity, we need to compute numerically. The numerical algorithm of KL consists of the following steps. First, we'll do the preprocessing for all input data to have identical norm to make sure marginal variance is identical. And then we'll consider 3 linear space for every layer. First, the pre-activation U from minus Umax to Umax, and you will have ng elements here. And the variance S from 0 to S max with ns elements, and correlation C from -1 to 1. You will have nc elements in this linear space. And then we want to recursively compute the KL of xx prime. It's equal to the delta w squared times the expectation of alpha li of x times alpha li of x prime plus delta b squared to your final layer L. So we need to compute the expectation here. And this is, as we mentioned before, it's a function f sigma of 3 variables. But because KL minus 1 x is equal to KL minus x prime, so it's in fact a function f sigma of 2 variables. So then we'll prepare a lookup table FSC to compute our f sigma. The FSC is, write it down as this. Below is the normalization factor, and we'll sum over different 2 pre-activation variables, UA and UB. Because UA and UB is considered from a multivariate Gaussian distribution, so the probability is proportional to exponential of this thing. So the FSC is in fact to consider the expectation value of our nonlinearity of UA times nonlinearity sigma of RUB. And in each layer, you will use the same lookup table FSC, and you will approximate F sigma by bilinear interpolation into FSC with here the S is equal to your previous layer KL minus 1 of XX, and SC is equal to the KL minus 1 of XX prime. And you will compute following the steps and iterate until KL. Now we'll check the experiment part. There are some experiments that compare the NNGP with similar neural network trained with SGD. The train and test are on MNIST and CIFAR 10 dataset. In this experiment, they use mean square error on one hot label with incorrect label set to minus 0.1 and correct label set to 0.9. The nonlinearity are tested with ReLU or hyperbolic tangent. The result is shown in the graph. Since the model performance is related to the hyperparameter selection of your weight variance delta W and delta B, so each line here is the best combination of those hyperparameters on a specified condition. The NN5, for example, the NN5 here means the hidden layer width is 5. So you will have a hidden layer from 5, 10, 50, up to 5,000. So you can see that for most of the case, neural network Gaussian process show the best performance. And the neural network gets better performance with wider hidden layer width. And they will finally approach the infinite width NNGP case. This table shows the accuracy of best performance of hyperparameter tuned model. Two models here are NNGP and NN trained with SGD. The first column is the training data set and the training data count. So we will have MNIST 1K, 10K to 50K, and CIFAR 1K, 10K to 45K. The nonlinearity will have ReLU or hyperbolic tangent. In each block, you can compare the best performance of NN neural network trained with stochastic process or NNGP. The two 5,000, 3.19 and 0.00 is the hyperparameter for layer depth, hidden layer width, and sigma W square, delta W square, and delta B square. And for Gaussian process, this is the hidden layer and delta W square and delta B square. You can see that in most of the case, NNGP outperform finite with NN trained with SGD. The figure here shows that many different initialized neural network with different width and then trained to 100% accuracy to check the generalized error. We can see that with ReLU as the activation, function, the performance is more concentrated to the low general error line. Here, it's more concentrated, and for the tangent, hyperbolic tangent, it's more separated. And also, the larger the width, the smaller the generalization gap. So this might suggest that an overparameter high-width neural network might generalize better compared with smaller width neural network. The last section we will talk about is neural tangent kernel. As shown previously, randomly initialized neural network with infinite hidden width is equivalent to a Gaussian process. For an infinitely wide fully connected neural network, the network function, that is, a function maps the input to the neural network output, follows the kernel gradient of the functional cost during training. This kernel is called neural tangent kernel. Neural tangent kernel is defined as below. It's the expectation value of inner product between gradient of the output function of the infinitely wide randomly initialized neural network with respect to its parameter. To understand the concept of neural tangent kernel, we will start with the dual space of a vector space. Given a real vector space V, then we have a dual space V star, which is defined as a set of all linear functions on V. For instance, f is a linear function from V to a real number. Then the function f is an element in dual vector space V star. A bilinear form B is defined as a mapping from two vector spaces U cross V to a field of scalar K. A metric is a symmetric bilinear form on the same vector space. That is, B a mapping from V cross V to K. And we can write that B of V, V prime equals to B of V prime V. A metric will establish an isomorphism between V and V star and gives a mapping from V to partially evaluated B of V dot. And this B of V dot is in the dual space V star. An inner product on V is a bilinear form, which is both positive definite and symmetric. So we can have the mapping from our V to its dual element. Then we consider in a function space F. The inner product on F, and given the function on this space, we can have a kernel and which can be evaluated on points x and x prime. So we can write k of x prime is equal to the inner product of f of x and f of x prime. Notice that the neural tangent kernel is a kernel with features in function space. By the way, the partial evaluation of kernel k of x dot is a function in this function space. Now, back to our topic. Consider a neural network function f of theta x. It's a mapping from Rp cross Rn0 to R. Notice that here the P is parameter numbers and N0 is our input dimension. For simplicity, we only consider R here, but it's not hard to extend to Rn space. And the expected loss L of theta is half of the average value of square of the difference between your predicted value f of theta xi and your ground truth yi. And the training data set is x and y. The neural network output evolved as formula below. The time derivative of your function f of theta xi, notice that the theta here is a function of t. So it's in fact theta of t. And it is equal to the inner product of your gradient of your function f and the time derivative of your theta. Because we want to optimize the loss, so dt over d theta over dt is equal to the negative gradient of your loss. So you can write it as below. It's the negative average value of the difference of your predicted value and the ground truth times the inner product of your gradient of function f of theta xi and the gradient of f of theta xj. So here, the inner product here, you can write it as a kernel matrix h of t. And we will later show that this h of t will converge to h star. And also, the h of t ij, it's equal to the kernel theta lt of xi xj, and the h star ij is equal to theta l infinity. This is the neural tangent kernel, as we mentioned before. And the L here means this neural network is with the depth is L, and T here is at time T. And the H star or the neural tangent kernel is a constant kernel. For the following steps, we need to describe the neural network setting first. Consider a L-layer fully connected neural network. We can write the prediction function f theta x recursively, and f of theta x equal to f l plus 1 of x, where the fh of x is equal to the weight wh times the gh minus 1 of x, and gh of x is equal to the normalization factor times the nonlinearity of your fh of x. Here, the w is IID from normal distribution with zero mean and univariance. And C sigma is the factor that related to your nonlinearity terms. And dh is the dimension of the width at that layer. Or you can expand the f of theta x, so it will look like this. Now we can compute h of t, the kernel matrix, if we compute the kernel theta lt of xx prime. At initialization, the theta is equal to every parameter at each layer, and they are generated from normal distribution. So we can have that the kernel theta L0 of xx prime is equal to the summation at each layer of the inner product of the gradient of f of theta x at each layer. And we can write it as the summation of every layer of the inner product between bh of x times gh minus 1 of x and bh of x prime times gh minus 1 of x prime. Here the bh of x is defined recursively as below. It's 1 for the last layer, L plus 1, and it's the normalization factor times the diagonal of the derivatives sigma dot of fh of x times the weight wh plus 1 times bh plus 1 of x at the rest of the layer. So it's defined recursively. And here we change the diagonal part to dh of x for simplicity. And since the inner product of gh minus 1 of x and gh minus 1 of x prime is equal to c sigma over dh times the summation of every node times sigma of fih minus 1 of x times sigma of fih minus 1 of x prime. And we change this will converge to the expectation value because this is the average, and this will converge to the expectation value as the width dimension dh goes to infinity. And we change to make it easier to see, so we change the function here to mu and nu. So this inner product will finally converge to the expectation value of c sigma times sigma of mu and sigma of nu. And the random variable mu and u and nu here is generated from a normal distribution. And we can write it as sigma h minus 1 of xx prime. And as for the inner product of bh of x and bh of x prime, it's approximately equal to this thing. The reason why we say it's approximately because we change the w to w tilde. You can see that the d here is from here, and the w h plus 1 is from here, and the bh plus 1 is from here. And this also goes here, and w goes here, and b goes here. So why we need the w tilde is because w tilde is a redraw of the w. And because we want our w tilde to be linear, to be independent to our bh plus 1 of x, so we draw it so it's approximately equal. And this value will equal to c sigma over dh and summation of sigma dot of fih of x times sigma dot fh of x prime, and times the inner product of bh plus 1 of x and bh plus 1 of x prime. The reason why we don't see W tilde here because it's univariate, so it's 1 here. And this overall, it will converge to a sequence of product, and as the dimension dh goes to infinity. So we'll change to mu and nu. So it will finally converge to this. And we can write it again to this one, the sigma dot j of x prime. It's a derivative of previous of the sigma we defined here. So finally, we can get the theta L0, our kernel theta L0 of x prime at initialization will converge to the neural tangent kernel theta L NTK of x prime. And we can write the neural tangent kernel as this formula. So this means that the finite neural network kernels will converge to a deterministic neural tangent kernel if the width of each layer goes to infinity. We can summarize the result in the theorem. The theorem neural network kernel metric converge to neural tangent kernel. If we fix the epsilon larger than 0 and the sigma is in the range of 0 and 1, suppose we have the nonlinearity is a Raloux function, and we have the minimum dh of each layer is larger than the order of L to the power of 6 and f over the epsilon to the power of 4 times log L over delta. Then we can have that for all x and x prime with the norm of our x is smaller than 1 and x prime is norm of x prime is smaller than 1, we have a bound with very high probability. The bound is that our neural network kernel at initialization minus the kernel of neural tangent kernel will smaller than L plus 1 times epsilon. So it means that the kernel, the normal neural network kernel will converge to neural tangent kernel if the dimension at each layer is very large. So we can write the kernel matrix h of 0 at time 0 will converge to the deterministic kernel h star. Now we can check the dynamics during training. The training dynamics is described by the time derivative of your function f of theta xi. Now we change the notation to time derivative of ft of xi. And it's equal to the average difference of your ft of xi predicted value to your ground truth yj times the kernel matrix h of t ij. And you can also write it in functions space. So it's an inner product of f star minus ft and the partially evaluated kernel theta lt of xi dot, and you evaluate the function over the training data x train. The f star here is the ground truth evaluated function, so it's f star of xi is equal to the ground truth yi. And it can be proved by the following theorem that the kernel perturbation during training is bounded. So for a fixed epsilon is smaller than a polynomial of 1 over L and 1 over N and minus 1 over log delta and lambda 0. Here, the lambda 0 is a positive number that bound the minimum eigenvalue of ht. So suppose we set the dimension of each layer, the width dimension of each layer to be m, and m is larger than the polynomial of 1 over epsilon, and kappa is smaller than 1. The kappa here is a multiplier to the output. That means the predictive function we will use is fnn. It will equal to kappa f. The f is our original function mentioned before. The reason why we need this kappa is because we want this fnn to be very small initially. You will notice that the kappa will not be used here, but it will play a role in the next theorem. And then for all t larger than 0, x and x prime belongs to is in from x1 to from your data set and x test. We will have that the kernel theta lt of xx prime will be very close to the initial value of your kernel theta L0 of xx prime with a very high probability. So it means that if we combine the previous theorem, that we can know the kernel metric h of t is very close to your kernel matrix in the beginning, and it is also very close to your neural tangent kernel, the h star. Therefore, we have the time derivative of ft of xi will be approximately to the average difference of ft of xj to yj and times the neural tangent kernel matrix h star ij. And now we set u of t to be the vector of all function ft of xi. And we can write the time derivative of u of t to be negative of h star dot u of t minus y. The y here is the vector of all training data. And since h star is positive definite, it can be proved that the positive definite could be proved if suppose the input value satisfies some condition, and we denoted the eigenvalue decomposition of h star as summation of lambda I, rho I transpose. The lambda I is the eigenvalue and the rho I is the eigenvector. And we multiply the eigenvector to both sides of this equation. Then we can have the rho I transpose u of t over dt is equal to the minus rho I transpose times h star dot u of t minus y. And this is equal to lambda I rho I transpose. So for each eigenvector component, this ordinary differential equation have a solution as below. The rho I transpose dot u of t minus y is equal to the exponential of the minus lambda it times rho I transpose dot u of 0 minus y. Note that from rho I to rho n form an orthogonal basis. So we can write the u of t minus y is equal to the summation of rho I transpose dot u of t minus y, and it's equal to the summation of exponential, the eigenvalue, minus rho it times rho I transpose dot u of 0 minus y. And from this equation, you can see that as time goes to infinity, the right-hand side goes to 0. So the u of t will converge to your training value, ground truth y. So the training error converged to 0, and the predicted function f NTK here converged to a kernel-rich regression with 0 regularization if the initial value u of 0 is very small and the width goes to infinity. So we can write here the predicted function for NTK f NTK of x is equal to the summation of the neural tangent kernel theta L NTK of xxi times the inverse of the kernel matrix H star ij times yj. And also, the decomposition representation is also a good motivation for early stopping. You can see that because for large eigenvalue, the exponential goes to 0 quickly. So if you stop earlier, those eigenvalue that did not drops to 0 will be the arrow term. We now summarize the close relation between fully trained neural network and neural tangent kernel regression with this theorem. Suppose our nonlinearity is ReLU, and we have our width dimension d1 to dl is equal to m. And m is larger than polynomial of 1 over kappa, l and 1 over lambda 0, n and log 1 over delta. And the 1 over kappa is equal to the polynomial of 1 over epsilon and log of n over delta. Then for any x test with x test have a norm is equal to 1, we will have that the predictive function of fnn of x test will be very close to the prediction of fntk of x test with a very high probability. It means that we can compute large width neural network function fnn through fntk kernel regression. The neural tangent kernel is not only for fully connected neural network, There are also extensions of NTK that to other types of neural network, such as CNN and attention layer. Both the training dynamics of infinitely wide convolutional neural network and infinitely multi-head attention layer could be described by its corresponding neural tangent kernel that are both defined recursively. That means the neural tangent kernel is a function at a neural tangent kernel at layer L is a function of your previous neural tangent kernel at layer L minus 1. So we can use this equation f NTK of x is equal to a summation of the neural tangent kernel theta L NTK of xxi times the inverse of h star ij yj to inference the prediction if you given an x. Here is the CNTK performance on Cypher 10. The CNN and CNTK here are simple stacking of CNN with or without global average pooling. A SIGNTK means the convolutional version of neural tangent kernel. And you can see that the performance for vanilla CNTK is close to CNN for different depth, and both getting better with global average pooling layer. Here is the attention layer neural tangent kernel performance comparison on IMDb review dataset. They compared the performance between NNGP and NTK with attention layer. Neural network Gaussian process and neural tangent kernel are both related to infinitely wide neural networks. Their difference could be described as NNGP is weakly trained and NTK is fully trained. Because for NNGP, every layer except for the top layer is trained by gradient descent, while for NTK, all weight will be trained by gradient descent. Finally, we will briefly introduce a library for NNGP and NTK. Neural Tangent is a library for implementing NNGP and NTK. The library helped to translate a neural network architecture into a sequence of kernel operations of NNGP or NTK. Recall that the equation for NNGP, the mean of our prediction function fgp of x prime given your testing data x prime and training data xy is equal to k tilde of x prime x transpose times the k inverse of k of xx times y. And the equation for NTK, f NTK of x is equal to the neural tangent kernel theta L NTK of xx times the inverse of theta L NTK of xx times y. Here's an example of how to translate a convolutional neural network into a sequence of kernel operation. Provided that we have 4 inputs, each with 3 features and 10 pixels. And the architecture, neural network architecture is 2 convolutional layer and 2 nonlinearity, and the final layer is a fully connected layer. And then to the final output. So for the kernel, we will compute the covariance. Because it's 4 inputs, so we need to compute the covariance of 4 by 4. And we will convert the convolution, nonlinearity, convolution, nonlinearity, and fully connected layer by layer, until we get the final kernel. Here's an example of writing code that converts your predefined neural network to an NNGP kernel. Here you define the neural networks, and then the library will help you convert this neural network to first the initial parameter of the neural network and the apply function for this neural network. And then the last part is the infinitely version of kernel of this neural network. So then you can use this kernel and assign this kernel to be NNGP, then you get the NNGP kernel for this neural network. Then we can use our previous kernel to inference infinitely wide version of NNGP or NTK given your training data. So suppose we have our training data X and Y and the test data X test. So we can train our kernel function with the given your training data. And you can use this predict function to predict the result of NNGP or the result of NTK. We can even create an infinitely wide version of ResNet. This part is the definition of ResNet function. And for the wide ResNet function, we have a widening factor k equals to 1. So apply this function, you will get the initial weight and apply function for the wide ResNet with widening factor k equals to 1. And also an infinite wide version kernel function. So for the infinitely wide kernel function, the k here equals to infinity. Here's a comparison of different widening factor ResNet to their infinitely wide NNGP or NTK prediction on CIFAR 10 data. You can see that for a larger widening factor or with more samples in Monte Carlo estimation, you can find that the difference between the wide ResNet to your infinitely wide version of NNGP kernel will be smaller. And also for NTK with widening factor, larger widening factor and larger sampling number, you will get a smaller difference between your neural network and your NTK predicted result. The last graph shows testing performance on CIFAR 10 of different NNGP and NTK. The fully connected NTK are the worst, and the convolutional NTK or convolutional NNGP are better, the orange one. And the wide ResNet, the green one, is the best. That's all for this talk. You can check reference for more detail about this topic. Hope to see you soon in the next video. Bye bye.